While measuring any one of two entangled photons, both always end with the opposite or same polarization. If both are same, they can be in two possible states, horizontal or vertical. And also, two possible states are there if both are different, horizontal-vertical or vertical-horizontal. If both of them are in the same state, then it's not in an interesting or special state because we cannot see the wave behavior here. Both will always exhibit the same state. This non-waving state is denoted by the Greek letter phi. The state of both are different is a really interesting one. The entangled photons flip-flop their state all the time and come to a definite state with opposite polarization to each other's only after the measurement. This waving state is denoted by the Greek letter psi. These two categories are subdivided by the rotational state. Remember, we saw in the earlier video that photons can be in the vertical state, which has fallen in the positive or negative region, and can be in the horizontal state, which also has fallen in positive or negative region. It starts with positive vertical state. When we rotate it clockwise, it goes through the positive horizontal state, next through the negative vertical state, then through the negative horizontal state, and finally reaches the initial state of positive vertical state after completing one full rotation. In this visual, we cannot differentiate positive from negative sides. Both look similar. So let's rotate with the axis of its edge. It will show some difference. Now we can see the difference between positive and negative vertical states, and positive and negative horizontal state as well. So the entangled two photons state of opposite polarization is subdivided by its rotational state, and we get these four different combinations. Opposite polarization with the same sign is causing positive wave correlation. Opposite polarization with opposite sign is causing negative wave correlation. Same polarization state has 6 possible combinations in which the 4 combinations are having the same sign and causing positive non-wave correlation. The other 2 combinations are opposite signs and cause negative non-wave correlation. This is a summary of all combinations with appropriate Bell states. The negative wave correlation state is different from the others. This is the only state that has opposite quantities in both polarization and sign. It returns 0 and claims singlet state. As the sign is changed while exchanging photons, it also claims the state of asymmetric. All others remain in the same state even when exchanging photon locations, so these all have symmetric state. Can we copy the exact state of a photon to another photon? It may be possible. Alice in Japan has one photon, and Bob in America has another one. Alice wants to change her photon to be exact replica of Bob's photon. Is it possible? Can it be done? Bob can measure his photon's polarization and can send the measurements to Alice. Then Alice can rotate her photon to the same direction. The task is completed. Both photons are now in the same state. Is there any flaw in this procedure? There are 3 phases here. 1. Bob measures his photon polarization. 2. Bob sends a message to Alice about the polarization direction. 3. Alice rotates the photon to the same direction. The third one is okay and possible. Alice can use wave plates to change polarization and rotational states. The second one is also okay. Bob can use any methods to send her the measurement information. The first one is quite difficult. Actually, it's quite impossible to measure photons' exact polarization direction. Photon polarization is invisible. We can find that it is vertical or horizontal or any other angle by using polarization filter. But the problem is that the polarization will be changed if we measure in the wrong direction. Assume that the photon polarization is 45 degrees. Now we need to measure it. Polarization filtering is the only way we have to measure it. Okay, in which angle can we measure the 45-degree polarized photon? Keep in mind that we don't know the photon's actual polarization. We can use a random angle. If we use vertical filter, then the photon will pass 50% of the time and will be blocked another 50% of the time. This measurement might change its original polarization. This is known as quantum no-cloning theorem. The photon state is completely forbidden. No one knows the exact polarization angle of a photon. I believe that engineers who engineered the universe purposefully hid it from human knowledge. Okay, this is the situation. Supporting one photon state to another is impossible by normal way, but it is possible in a quantum way. Yes, quantum entanglement can make this porting possible. Let us see how quantum teleportation works. Bob creates two photons, A and B, which are entangled. He sends photon B to Alice. Both A and B are still entangled, even parted by a long distance. Later sometime, Bob has another photon, C, and wants to teleport that to Alice. In simple terms, he wants to copy the state of C to photon B. This is the procedure. Photon A and B are already in the entangled state. Whatever the measurement made on photon A will affect photon B instantaneously. So if we create the entanglement between A and C, then photon C's polarization will be transferred magically to photon B. The previously entangled photons A and B are disentangled now. Now the photons A and C are in the entangled state. We still don't know what the polarization states of photon C is, but old polarization state of C will be transferred successfully to photon B. But still the entire state is not yet copied. Yes, we successfully transferred the polarization, but the rotation state is not yet copied. We will see how to recover the rotational state later. Now, let's see how to create entanglement between photons A and C. Hong-Ou-Mandel effect will make two individual photons entangled. In this method, a half-silvered mirror-based beam splitter which reflects or transmits photons with 50-50 chances is used. This beam splitter has two input channels and two output channels. Two photons are superimposed by sending each one into each input channel simultaneously. The two photons are interfere with themselves and become entangled. While coming out, it uses both or same output channels. If both photons have the same polarization, then both always come out through the same output channel. There are four possible ways for two photons to interfere in this beam splitter. Both of them get transmitted, both of them get reflected. Upper channel photon is transmitted, and bottom channel photon is reflected. Or the upper channel photon is reflected, and bottom channel photon is transmitted. 1 and 2 are used if both photons have different polarization and different rotational state. 3 and 4 are used if both photons have the same polarization or same rotational state. We created entanglement between photon A and photon C. Now the polarization of photon C has been successfully transferred to photon B. But still the teleportation is not fully completed. For that to happen, the photon B has to have the same rotational state as photon C. See this photon. It is vertically polarized. We don't know its rotational state. It may be positive or negative. The rotational state is applicable to all three dimensions, x, y, and z, which gives 4 different types of rotational states. Let's see the photon z basis. It will give better differentiation among 4 rotational states. First one is not rotated. Second one is rotated around the x-axis. Third one is rotated around the y-axis. And the fourth one is rotated around the z-axis. So we need to find photon C's rotational state and send the information in the classical way to the holder of photon B. Then photon B has to be rotated accordingly. Keep in mind, rotating photon will not change the photon's existing polarization, and the superposition will be kept. How can we find photon C's rotational state? Rotational state can be identified by the Bell state of two entangled photons A and C. The first Bell state of negative wave correlation denotes that both C and B are same, so no rotation is needed. Positive wave correlation denotes that B has to be rotated by 180 degrees around the z-axis. Negative non-wave correlation denotes that B has to be rotated by 180 degrees around the x-axis. Positive non-wave correlation denotes that B has to be rotated by 180 degrees around the y-axis. How do we find the Bell state of these photons A and C? The result of polarization measurement after Hong-Ou-Mandel effect will tell us about the Bell state of photons A and C. The beam splitter has two output channels. We can measure the polarization of photons which come through output channels by setting up polarized beam splitters. Polarized beam splitter splits the photons into two different directions based on its polarization. Vertically polarized photons go up and horizontally polarized photons go down. There are two output channels, upper and bottom, and each channel has the polarized beam splitter. So these are the possible paths of a photon ending up with UH, UV, BH, and BV. These are the possible signatures for two entangled photons, and the Bell state is identified by these categories. Unfortunately, this Bell state measurement method doesn't differentiate the correlation of negative non-wave from positive non-wave. It is incomplete Bell state measurement method. We can succeed only 50% of the time using this method. Here's a cheat sheet for quick reference. I will explain the complete Bell state measurement method by another video. We cannot see these signatures. Why? Because same polarized photons can come only through the same channels. We measure the polarization of A and C. Doesn't it affect the photon B, which was previously entangled with A? No, both A and B are disentangled state now, so photon B still keeps the superposition state. As we measure A and C, they lose their superposition state, so the source must be destroyed in quantum teleportation. So based on the Bell state, photon B is rotated or not rotated. Bob has photons A and B, which are entangled. Bob sends B to Alice. Later, Bob has another photon C and wants to teleport the C state to photon B, which is now with Alice. So Bob entangles photons A and C by the HOM indifference method. B acquires the polarization of C, and it disentangles from A. Now both A and C are in the entangled state. Bob further measures the polarization of A and C and finds the Bell state. Then he sends two bits of information, which donate the Bell state to Alice. Alice rotates the photon by appropriate wave plates, based on the instructions received from Bob. That's it. Teleportation is successfully completed. But you know what? Teleporting matter particles is also possible by this way.